Okay. So, we need to finish, and then we're going to create a conclusion. And hopefully, this whole thing, this whole write-up will be the model for you to be able to use throughout the rest of the year, so you can be able to start doing these things on your own rather than spending several lab periods creating it every time. Okay, so the last thing that we needed to do was determine a percent yield. And what was our last step? What was the number of the last step?
27.
27, wow. Determining percent yield. When I'm determining a value of something, I'm usually going to have some kind of a formula, just as we did with the beginning. And can I get one of you to shut the door for me there? Just as we did with the grams thing, I need a procedure to tell me how to accomplish this. And it's easier to work with grams than it is to work with moles. But it should turn out the same. If I were to say the percent yield based on the number of moles, right? The percent yield is an amount of particles. The number of moles is an amount of particles. So the percent yield based on the amount of particles should work out to be the same as the percent yield based on the number of grams. Working the number of grams is a lot easier, though. So we're going to do that. What would I want to say is a formula that will determine the percent yield for me? What is the percent yield again? Remember, I'm supposed to get a certain amount, but I got a different amount.
Would you take your projected amount and divide it by the actual amount and put that here?
That would give you more than 100%. So yeah, I want to take so write out the percent yield formula. And this is typically something you would have in a data table, right? Write out the percent yield formula, and you're going to say percent yield equals amount, or we're going to say grams obtained divided by grams expected. Times 100, right? Grams obtained divided by grams expected times 100. That'll give you the percent yield. And we'd like it to be 100%, right? We would like the amount that we got to be exactly how much we expected. We'd like the amount we got to be more than the amount that we expected, right? But that's not going to happen. So how did we figure out the amount obtained? How did we figure out the amount that we obtained? We just masked it, right? We just masked the amount that we had. We have this little data table up here somewhere. Oops, wrong way. And we should probably add something to the data table down here that says percent yield equals grams obtained divided by grams expected times 100. How many grams so I'm just going to do this for one of you. What was, Aspen, what was the mass of the precipitate in your group?
2.87.
2.87 grams. Okay. Now, did we figure out yet what the grams expected is? Do I have that information? So our process, when we're dealing with any formula, oops, wrong way. Our process when dealing with any formula is to inspect formula to see if we have all information. Okay? Inspect formula to see if we have all information. And we're always going to have the amount obtained, right? That's part of our procedure above. We're always going to have that amount. But we don't have the amount expected. Okay? So what formula do I know that will give me a number of grams? I want grams expected. What formula do I know will give me a number of grams? Okay? If you do not have grams expected, write out grams formula. Grams equals moles times molar mass. Okay? So if you do not have grams expected, write out gram formula. Grams equals moles times molar mass. And we're going to do this in our data table.
So the percent you want to choose our numbers or the numbers you?
Your numbers. Yeah, for you guys, whatever your lab group got, okay, you're going to use your numbers. Okay, so how am I going to figure out what the number of moles we expected is? Okay, and did we already figure that out at some point? So, sorry.
Yeah, it's in the.
What?
Numbers.
If you do not have grams.
Okay, let's go back to our balanced chemical equation.
Right, gram formula.
Okay, but we've already actually done this. If I know the number of moles of lead acetate that I started with, don't I also know the number of moles of lead iodide that I'm supposed to get? Okay, so we can say get moles expected. Maybe we should modify this. Let's as we're thinking through this, sorry I keep going back and forth. Let's modify this just a little bit. Okay, it's not just moles, it's moles expected, right?
So would it be grams expected equals moles expected times?
Okay, let's even go that farther. Let's go that farther. Let's go that far. Okay, grams expected
equals moles expected times molar mass. Okay? So, and that's why I like this process of sort of thinking about this as a whole group. We're coming up with things that we should probably include on our own. We're not just depending on Marshall to say everything, okay? So that's a great idea. Grams expected equals moles expected, but it's still the same formula, right? Grams equals moles times molar mass. Okay? So if you do not have expected, grams expected, write out gram formula. Grams expected equals moles expected times molar mass. Determine moles expected from balanced chemical equation. Okay, this is one of the single most important points of the whole laboratory. Okay, how do I know what I am expected to get? How do I know what I'm expected to get? If I go back up to my, and I'll go back so you can finish writing it, but if I go back up to my balanced chemical equation, this is everything for us. If I start with 1 mole of this, I'm supposed to get 1 mole of this, because that's what the balanced chemical equation says. There's a 1 there. It's an invisible 1, and there's an invisible 1 there. My balanced chemical equation tells me how many moles I'm supposed to get. But if I start with 0.1 moles of this, then I should get 0.1 moles of this. How many moles of lead acetate did we actually start with? We figured that out in our data table, didn't we? Okay, so moles of lead acetate equals molarity times liters. We started with, we wanted a 0.1 molar, and we wanted 0.1 liters of it. So 0.01 times 0.1 times 0.1 gave us 0.01 moles. So if I started with 0.01 moles, I should get 0.01 moles of this. So this is how my balanced chemical equation helped me determine the number of moles expected. So now I can go back down here, and in my data table, let me rewrite this. Grams expected equals moles expected times molar mass. Now I know what my grams expected is, or my moles expected was. That's 0.01 moles. And I also gave you the molar mass. Oh, I didn't give you the molar mass of potassium iodide, did I?
You did.
Oh, I did of potassium iodide, but not of lead iodide.
You did both. And you did both. It's 379.24.
Oh yeah, because that's how we calculated that.
That's the lead acid. Oh, so how much was it?
For the lead acetate, it's got to be 379.24.
But we're not doing lead acetate. What is it that we got? We got lead iodide, didn't we?
Yeah, we got the right moles. Or actually, we did get the right moles.
We got the right moles, but we didn't get the molar mass yet. So, determine moles expected from balanced chemical equation. Determine right? Determine molar mass. Okay. determine molar mass in, I'm just going to say determine molar mass in usual way. So now I'm going to have to write this down. Molar mass of lead iodide right? Because this is our precipitate. I didn't give you this molar mass. Molar mass of lead is 209 or 207. I think it's 209, isn't it? Somebody look up the molar mass of lead for me. And the molar mass of iodine. What's that?
207.2.
Oh, 207 for, okay, so 207.2 for lead plus 2 times molar mass of iodine.
I'm getting 126.9.
120 what? 0.90. Okay, so now somebody calculate 207 plus 253.8. $460.6. Or I'm sorry.
This is.
No, 461.
I got 600.
I need 461.
Okay, so 2 times 126 is 253.8, right? 253.8 plus 207 is going to give me 461. So 461 grams per mole. So we plug that back into our molar mass here. And I'm just going to move my decimal places 2 points to the left, right? So I get 4.61 grams, okay? I expected 4.61 grams.
Marshall, ours are super close. Yeah. We got 3.9. Yeah.
You got 3.9? That's not super close. It's closer than 2.87, but it's not super close.
What? 7, 1, pretty close.
So 3.9 is close to 4.6? Not really.
3.7.
So what was your percent?
We have 84%.
Okay, well, that's not like 95%.
Yeah, but it's pretty close.
About 95.
If I round up, it's 85, but I'm not rounding.
Okay, so let's make sure we have all our procedural steps correct. Yeah. Okay, so our process was write out the percent yield formula. We inspected the formula to see if we had all the information. The information that we wouldn't likely have is the grams expected, right? So if you do not have grams expected, write out that formula. Grams expected equals moles expected times molar mass. Well, wait a minute. I don't have moles expected, so I can determine moles expected from the balanced chemical equation. And we did that. We found out that we needed 0.01 moles because that was the same as the number of moles of the reactant. We determined the molar mass of lead iodide. We plugged the moles and molar mass to find the grams expected. We plugged the grams expected in, obtained and expected in to find the percent yield. Okay, and all of that should be in a data table somewhere. Okay, so one of the things that you will learn to do then is as you create your procedure is going to help you figure out what you need to put in the data table. Okay, as I created the procedure, the first thing in the procedure said, make these solutions. Well, how do I make these solutions? I have to know how many grams to use to accomplish that. So in order to make those solutions, my procedure directed me to say, I need to put this in a data table. How do I make those solutions? How do I find out what those, so the number of grams are? Grams equals moles times molar mass. Well, do I have moles? No. Moles equals molarity times liters. Did I have molarity in liters? Yes, I gave you that information. So I can figure out what these two masses were. The procedure directed us to do this. The next place the procedure directed us to create some data was to figure out how much precipitate I got. And in order to do that, I had to write out the mass of the unused filter paper, the mass of the filter paper with the dried precipitate, and then the mass of the precipitate. Data table, okay? The procedure directs that. Now, a lot of times you'll find out that when you get into a laboratory situation, you have to kind of work back and forth between the procedure and the data table. Or you have to work back and forth between messing around with the equipment and creating the procedure. A lot of times you don't know what your procedure is going to be until you actually see the equipment and really sit down and think about the process. I will always make it when we have a lab so that you have an opportunity to create a reasonable procedure. And if there's something that's not going to be totally obvious to you by looking at the equipment or by reading through the pre-lab stuff, I will make sure that you're aware of that information and so that you'll know how to create a procedure. Okay? Again, I don't expect perfection until near the end of the year. This is going to be an evolving process. But hopefully by the time we get through everything at the end of the year, you'll have a really, really good idea how to create lab write-ups so that when you go into chemistry in college, if you go into chemistry in college, and I realize that a lot of you aren't going to, that's not where you're headed, but by that time, hopefully some of these other skills will transfer into other things that you might have need of. So any questions about the procedure here? Okay, so we have one last thing to do then, and that's create a conclusion. And hopefully we can accomplish that by the end of class, because I really am tired of this this lab. Determination of percent yield of a precipitation reaction was our title. And I changed our purpose a little bit. What we ended up doing in this was we used this to learn how to write a lab report and develop skills in preparing solutions right? We developed some skills in preparing solutions. In separation of mixtures, right? We used a filter to separate the mixture, and then we developed skills in learning how to determine the percent yield of a chemical reaction. So this is something that we'll have available to us throughout the rest of the year. These are things that we'll have in our toolkit, okay? We do need to write down all of the materials that we used, okay? So trying to put them in somewhat of an order in the way that we use them. The first thing we did was made solutions, right? So what things did we need in order to make our solutions?
Maybe the digital scale to
Lead acid.
Okay, so we needed a balance, and so we'll say the electronic balance.
You say.
Okay, what do we usually put on an electronic balance so that we don't get crap all over it?
Paper.
White paper. And we just used a sheet of paper. They actually have a special type of wax-coated paper for that we could buy, but it's more expensive than we want, so we just use regular paper. And then what did we weigh on it? So lead acetate. And it would be good to write out the name and the chemical formula, PbC2H3O2. And then what was the other reactant? Potassium iodide. Oops, doesn't start with a K.
Right on the data, and then you're going to
Okay, what else did we use to make the first solution?
the measuring spatula.
Oh, okay. So we needed a spatula. Forgot about that, thank you. What else? So,
With the lead acetate, we just used the Erlenmeyer glass. There we go.
Or no, we did the,
glass.
okay, we used the volumetric flask, and how big was it? What was its volume? 100 milliliter volumetric flask. Okay.
We used the Erlenmeyer glass.
Okay. So we needed 250 milliliter Erlenmeyer flasks.
We run like a 500 milliliter beaker as well.
Okay. What did we have in the 500 milliliter beaker?
Just water.
Water. Was it a 500 milliliter beaker? We don't have 500 milliliter beakers.
And it was probably like 250 something. I don't know.
It was actually a 400 milliliter beaker. And we just put water in that, right? What kind of water did we say we should have used? Deionized. We used tap water. We should have used deionized water. And again, the reason that we should have used that is because tap water has lots of chlorine in it. And anytime I try to dissolve something that has lead in it, the lead reacts with the chlorine and forms a precipitate called lead chloride. And it's what gave it that kind of white, cloudy appearance. And it didn't really decrease our yield by enough for us to worry about. But it would be an issue that you would want to talk about in your conclusion, maybe. What else did we use?
Graduated by half.
Okay, and what size was that? 25 milliliter. Graduated like that. then,
The ball.
oh, yeah, we used a pipette bulb, right?
Yes.
You said the ball? Who said that? Oh, good job.
Thank you.
And then we also, I heard someone say the disposable pipette. And what else do we need?
Funnel on the filter piston.
Okay. Funnel. Oops, and filter paper.
We also use an oven too, right?
Okay, we should have used the oven, or we would have if we'd have had time, but we just let it air dry. So let's call that a drying oven. Is that it? Okay.
Throw in goggles and.
Well, generally you don't put that, you just put that in the first step, okay? So, when you actually sit down and do this and try to think about this, a lot of stuff comes together. What you just did in lab, when you simply even just write out all the materials, it's like, oh yeah, I used that, oh yeah, I used that, oh yeah, we did that. And it really kind of pulls a lot of stuff together. Okay, but it's tedious and it's time consuming and it's annoying at the same time. So I understand one of the things that I hated the most about my college chemistry laboratory was writing all this stuff down. The documentation is really, really annoying. And even though the trend is towards more electronic kinds of ways of recording things, in a real laboratory, a lot of times you're still going to be required to write this stuff down as opposed to typing it out. Why might that be? Why might it be more important for us to literally write all this stuff down than type it into a computer? Yeah.
Because when you write it, it goes in your mind.
Okay, well that's a good point. That's one thing. But as far as documentation goes, what can you do to electronic data that you can't really do to handwritten data?
Read it all. You can steal and publish a lot easier online.
Okay, well that's true too. But you can't fake it. You can't go back and change things after the fact. There's a way that you're supposed to do things. If I had this list of stuff here and I said, oh, wait a minute, it wasn't a 300 or 400 milliliter beaker, it was a 1,000 milliliter beaker. You can't go back and erase this. That's basically illegal. It's not really illegal, but it's unethical. I need to keep this here, and what I need to do is put a single line through it and then write the thing down that I'm supposed to use, and I'm supposed to initial it and then date it.
That's just a revision process.
Okay, so writing things down makes it much more difficult to go back and change after the fact, and it makes it more difficult for you to cheat on things. So it's unethical to go back and erase things or cross it out so no one can read what you put originally. Okay, so I don't know how long that'll continue, but if you work in a real laboratory at some point in time, you're probably going to have to get used to writing everything in a laboratory notebook rather than typing it into a computer. Okay, although the way the trends are going, did you guys have to learn how to write cursive when you were in grade school?
Yeah.
Yeah. Okay. So, but they're not doing that anymore, are they? Writing things is a problem anymore. Okay, let's knock out a conclusion here. Okay? We have 4 main paragraphs to our conclusion, right? We have 4 main things that we want to talk about. Our first paragraph says, this is what we did. This is what we found. This is what we did. This is what we found. Okay? This is what we did. This is what we found. Our second paragraph talks about the chemistry of what you did. The third paragraph talks about the possible sources of error. And the fourth paragraph is a summary that says, this is what I learned. In conclusion, I learned this. Okay? So, what did we do? This is what we did. This is what I did. What did we do? What's the title say that we did? Okay, we determined the percent yield of a precipitation reaction okay, but we want to add a little bit more information here than what we added in the title. We determined the percent yield of a precipitation reaction.
Specify which precipitation reaction you did?
Yeah, I want to add in the fact that it wasn't just any old precipitation reaction. I want to tell you what the precipitation reaction was. So how might we say that? We determined the percent yield of a precipitation reaction
Lead acetate and that's right.
Okay.
It's the precipitation reaction between or of something.
Okay. The precipitation reaction resulting from the addition of a let's even be more specific, resulting from the addition of 0.1 liters of a 0.1 molar solution of lead acetate. So we determine the percent yield of the precipitation reaction resulting from the addition of 0.1 liters of a 0.1 molar solution of lead acetate and 0.1 liters of a 0.2 molar solution of potassium iodide, right? This tells us exactly what we did, right? I did this. We determined the percent yield of the precipitation reaction resulting from the addition of 0.1 liters of a 0.1 molar solution of lead acetate and 0.1 liters of a 0.2 molar solution of potassium iodide. I did this. We found this. We found, okay, what kind of information might I want to put into that? We found.
I guess the process didn't have a full yield.
Okay.
Wouldn't be expected yield.
We found that when we added two chemicals, bright yellow precipitators.
Okay. So,
Are we going to put, that we did a chemical equation, we found the molars of,
that would go into the chemical, the chemistry part. Okay? I just want to, in the first paragraph, I just want to tell people this is what we found. We did this and we found this. Do I want to put in anything about what we expected to find?
Yeah.
Okay? So, and you can write this in 1,000 different ways, right? If I sat down and wrote this out again tomorrow, I would put different words in here. We, what's that?
We expected 4.61 grams of precipitate occurring from the reaction.
Okay.
Instead of our expected.
Is there a better word than expected? Is that what you asked?
No, I'm just switching it around. Like,
Oh.
instead of how I expected, well, you found this. Okay.
So maybe we want to put that in a little bit of a different way. Sorry about that. Although we expected and how many grams was it? 4.61 grams. And let's say a bright yellow precipitate. Although we expected 4.61 grams of bright yellow precipitate. We found, let's see, we produced, okay, good job. We produced, and this would be where you put in your own number of grams. Okay, we produced grams. We produced blank grams for a yield of
what would be a percent yield?
For a yield of this percent. Okay? Okay? This is really pretty simple, right? This is what we did, this is what we found. Okay? This is what we did, this is what we found. That's all you need to say in that first paragraph. Okay, this is what we did, this is what we found.
Oh, there's the back. Yeah, I can go to that. You what?
Yeah, there's a lot on the back.
I know.
Okay, obviously I probably gave you a little bit more than we need to. But this is what we did, this is what we found. Any questions about that? This is how all of your things should read. Now, this is not all of what our purpose was it? We also had a purpose of, we wanted to learn about making solutions, we wanted to learn about separating mixtures, we wanted to learn about how to create a percent yield. All of that stuff will be part of your conclusion that says, in conclusion, we did this, but we also, while we accomplished this percent yield thing, we also learned about how to do, these procedures and things. Okay? So, in the second paragraph, we need to talk about the chemistry of this. We need to talk about the chemistry of this. And we said that the type of reaction that we had was a double replacement reaction. It's also called a precipitation reaction. So we're going to need to talk about that. And I guess a good place to start would be by simply saying what the chemical reaction was. And so Aspen asked that question, are we going to say anything about the specific chemical reaction? So in this second part of this, and I'm going to direct this a little bit more, we need to say we did this chemical reaction. So we might just start off by saying the chemical reaction forming the basis of our procedure is, and then you can put a colon there if you want, or you can just leave it, is PB C2H3O2 plus 2Ki gives us lead iodide plus potassium. Oops, I don't need to erase C2H3O2. Okay, so the chemical reaction forming the basis of our procedure is this. Okay? And we've called this a double replacement reaction. We've also called it a precipitation reaction. And we also said that we should say what the state is. That's an AQ there. I should put, after this, I should put a little AQ there for aqueous. I should also put a little AQ here for aqueous. Okay, that means it's in solution, right? Aqueous means that it's in solution. We should put an S here for solid after the lead acetate, or after the lead iodide, and then aqueous again here. Okay?
Isn't the potassium acetate have a 2 before it? Because we get 2 acids.
Oh, you're right. Thank you. Right? Okay? And one of the next things that we're going to learn how to do is balance chemical equations thoroughly. Okay? Okay, so the chemical reaction forming the basis of our procedure is this. This is a double replacement reaction in which this is a double replacement reaction in which we change the cations, okay? We're going to switch the lead for potassium, and that's exactly what we did, right? We switched the lead for the potassium. So this is a double replacement reaction in which the two cations switch anions. Okay, that's what all double replacement reactions are going to be. I'm going to have an ionic compound here, and I'm going to have an ionic compound here. And anytime I have that situation, if I write that equation out, the expectation is going to be that the two cations switch anions. Okay? The two cations are going to switch to anions. This usually results in one of the products being insoluble and precipitating out. Okay? This usually results in one of the products being insoluble and precipitating out. So I'm telling my audience, or whoever might read this, what the chemistry of this is. Why is this happening? In this type of a reaction, whenever I get two ionic solids or two ionic substances that are dissolvable, and both of these are dissolvable because I've said they're both dissolvable, right? Anytime I add them together, I'm likely to get a new substance that precipitates out. What happens to the other substance? Stays dissolved, right? It stays in solution. Okay? This usually results in one of the products being insoluble and precipitating out, while the other...
If you wanted to, could you precipitate the other one out?
It wouldn't work. So if I have two substances here that are going to always dissolve, right? Both of these substances are always going to dissolve. Only one of them will actually end up precipitating out. The other will still form a substance that will always stay in solution.
Unless it's evaporated.
Well, if you evaporated it, then it would come out of solution, right? So, yeah, if I separated the lead iodide out, and then I let the remaining substance evaporate, then I would end up with a bunch of potassium acetate that's solid. Yes, exactly. So, and precipitating out while the other remains in solution. Okay, so this is a double replacement reaction in which the two cations switch anions. This usually results in one of the products being insoluble and precipitating out while the other remains in solution. Okay? So our goal in this reaction was to determine the percent yield. So what we could then say is something about, we've already said as much as we need to say about the reaction itself. Okay? Now I want to say something about how we figure out what the percent yield is. Okay? We can determine the percent yield of such a reaction by evaluating and I'm going to use a word that I think we've probably used once so far this year. When I look at the study of figuring out how many moles of one thing reacts with the number of moles of the other thing, does anybody remember what that study is called? Stoichiometry. Okay? We look at the stoichiometry. So we can determine the percent. Oh, I should have put the word yield in there, right? Okay, sorry about that. Okay. We can determine the percent yield of such a reaction by evaluating the stoichiometry of the balanced chemical equation. Okay, we can determine the percent yield of such a reaction by evaluating the stoichiometry of the balanced chemical equation. Knowing the number of moles, of either reactant used. Okay, that's what we did, right? I could do this, I could figure this out knowing either that this is 1 mole or this is 2 moles. I could say the number of moles of this has to be 1/2 of the number of moles of this, right? If this is a 1 and this is a 2, the number of moles of this would be 1/2 of the number of moles of this. So I could ask you to figure this out using the number of moles of either of the reactants. Or I could have found out how many moles of this I got, right? I could have done what Garen suggested and evaporated all of this solution and found out how many moles of this that I was supposed to get and figured out how many moles of this I was supposed to have. If I have 2 moles of this, I'm supposed to have 1 mole of this. So this is why we need a balanced chemical equation, so I can do all kinds of things with this stoichiometry. I can figure out everything I need to know about this by knowing something about this, or knowing something about this, or knowing something about that. Okay? So, knowing the number of moles of either reactant, the number of moles of product expected can be determined. Okay? Knowing the number of moles of either reactant, the number of moles of product expected can be determined. Okay? Knowing the number of moles of either reactant, the number of moles of product expected can be determined. This can then be used to find the number of grams expected. Dividing the number of grams obtained by this will give the percent yield. Okay, so knowing the number of moles of either reactant, the number of moles of product expected can be determined. This can then be used to find the number of grams expected. Dividing the number of grams obtained by this will give the percent yield. Okay. Have I pretty much said all I need to say about what the chemistry of this was? I think so. I could talk about how we accomplished making the procedures, but that's probably going to be more a thing related to our possible sources of error. Okay? Dang, it's getting late, isn't it?
Are we going to write the purpose of why we did it?
What's that?
Are we going to write the purpose of why we did it, like in a separate paragraph?
Yeah, that'll be in the conclusion part of it. Okay, so, and you'll find that in this particular case, one part of what we did is more appropriate in one of the paragraphs, and in another circumstance, it might be more appropriate in one of the other other paragraphs. Okay, but not yet. We've got to finish it. So we still got a little bit more. Is the way that we're doing this making any sense? Is this going to be useful for future labs, maybe?
Yes.
Or it just really sucks and I don't really care? That's okay. We're waiting until we're completely done.
Oh, so we're not turning.
No, not right now. I want all of it handed in at once. Yep. Okay, you guys are awesome. This is hard, but you're doing a great job.